tutorial, and then you'll have other tutorials. Okay, tonight we're going to talk about induction, we're going to talk about summations and logs, and we're also going to talk about arithmetic proofs. So let me write that here. So induction is a method of proof, and we're going to be using induction to prove lots of statements are true for large sets. So we've been talking about finite proofs where we have variables, like 4 variables where we're combining and doing logic proofs, and we're going to find one thing is true. But if we want to prove something is true for a large set of things, then we need to use a method that will show that something is true for all, say for all numbers, without us having to sit there and demonstrate everything. So for example, let's see, let me do prove n squared minus n is always even. So there's a problem that we're going to do, and I'm going to show you 2 different ways to do it. One way we're going to do is called by arithmetic proof, and one way is by induction. So anytime you have something that's fairly simple like this, you should be able to do it with an arithmetic proof, but you can also prove anything that you want to prove for all numbers, such as all integers maybe. You can also do it by induction. So first let's do it sort of arithmetically. So what does being even mean? Divisible by 2. So I could write it as a product of 2 and some other integer, right? So that means that I would be proving that n squared minus n is equal to 2k, where k is in the integers. So one way I could do that is by considering whether n was even or not to begin with. Does that sound reasonable? I could think if it was even, then obviously n squared minus n would be even, right? Because that's a sum of 2 even integers, or a subtraction of 2 even integers also. So let's consider the case 1. Case 1, n is even. And we know there's only 2 cases. It's either even or odd. So if n is even, let's say that's equal to 2j. Because that's the definition of even, is that it's a product of 2 and another integer. So if n is equal to 2j, then n squared minus n is equal to 4j squared minus 2j. And so if I want to prove that this is even, I have to be able to factor out a 2. Because we know that integers are closed under addition and subtraction. So if I add 2 integers, I end up with an integer. If I subtract 2 integers, I end up with another integer. So these things here, it's still an integer. This combination of numbers and letters is still an integer. If I can factor out a 2, that's equal to 2 times 2j squared minus j. This number here is an integer, right? Because j is an integer and so is 2, and these combinations of multiplying, adding, and subtracting them are integers. What's the only operation we normally do that isn't closed for the integers?
Division.
Division, right? If I divide 2 integers, I don't necessarily end up with an integer. So now that I've written this as 2 times an integer, therefore n squared minus n is even for this case. So all I have left is to prove that when n is odd, I still have n squared minus n is even. Okay, so I have one more case.
J is an integer. I mean, couldn't it be like 1/2 or?
That's something I assumed here. J is an integer. If n is even, it's the product of 2 and some other integer.
Okay.
So that was an assumption. When I wrote that n equals 2j, I was assuming that j was an integer, because otherwise n wouldn't be even. So if I write an even number as 2j, how do I write an odd number? Odd numbers are definitely not divisible by 2, right?
This one.
So I could put 2j plus 1, and that would be always an odd number, and every odd number I can write that way. Right? If I pick the right j, I should be able to write any odd number in the form 2j plus 1. So let's do case 2, where n is an odd number. So that'll be case 2. And the final case also. So n is odd. That implies that n equals 2 times j plus 1, where j is a member of the integers. In that case, then we want to see what happens to n squared minus n. So we're going to plug in 2j plus 1 for n and square it, and then subtract 2j plus 1. And we want to be able to factor out a 2 in the end. That's the whole goal. So this is going to be equal to 4j squared plus 4j plus 1 minus 2j minus 1. So that looks pretty good because our plus 1 and minus 1 are going to cancel, and then everything left is divisible by 2. But just to make everyone happy, we'll combine those j terms to get 4j squared plus 2j, because I have 4j minus 2j, and that's equal to 2 times the quantity 2j squared plus j. And we're happy because this is an integer, and we factored out a 2, so therefore n squared minus n is even. And since for both cases we have that n squared minus n is even, then we know that n squared minus n is always even, because all integers are either even or odd. Trick question, is 0 even or odd?
Neither.
Well, it can be divided by 2.
You have to, it's a tricky question, right?
Right.
Would I write 0 equal to 2j, or would I write 0 equal to 2j plus 1?
0 equal to 2j.
I would pick this one. Because there's no j I could plug in there and get 0. I can plug j equals 0 in there and get that 0 is equal to it. I can divide a 2 and have a remainder of 0, and that's really the definition of even, is if I divide by 2, I have no remainder. So 0 is an even number. It's not positive or negative, but it is even. Okay, so that was an arithmetic proof. In arithmetic proofs, we break the integers into groups of numbers, and then we prove the property that we want for every single group, and then once we've proved it for every group, we're done for all of the integers. So we can do that. Here we were talking about divisibility by 2, so if I wanted to show that some combination of letters together was divisible by 3, I would break n down into 3 cases. I would talk about n equals 3k, n equals 3k plus 1, and n equals 3k plus 2. So I'm not going to do an example like that today, but what I am going to do is a proof by contradiction, an arithmetic proof by contradiction. So that was a direct proof, a direct arithmetic proof. Let's do an indirect one. So far we've seen indirect proofs and we've done proof by contradiction. It's actually one of the strongest methods of proof for mathematics. The reason for that is it's a lot easier to come up with a counterexample than it is to prove a lot of stuff, right? So it's a lot easier to show that something's wrong than to show that something is always right. That's just like the difference between for all and there exists. It's a lot easier to find a there exists that would make a for all false than it is to show something for all. And that's why proof by contradiction is very, very important. So let's prove that the square root of 2, actually just make it square root of 3, is irrational. So who knows what irrational means?
It's like an imaginary, is that what you mean?
Well, what is rational?
Irrational.
A rational number is a number that can be written as one integer over another, as a fraction. So rational numbers, first we have to know all the definitions before we can solve a problem. That's very important in anything in computer science or any science or mathematics class that you have. You need to understand all of the terms in the problem before you get started. So that would be the first thing I would do if someone came to me with a question I'd never seen before. I would look up every word and find out exactly what it was asking me first. So a rational number is equal to a number that can be written like P over Q, where P and Q are both in the integers. And just for the sake of making things simple, let's also say that we're going to reduce this. For our representation, we want this to be the smallest one, because if I want P over Q to be unique, I have to specify that P over Q are divided out. All the common factors are divided out, because otherwise then I could have 1/2 is equal to 2/4 is equal to 3/6, and so on and so on. So if I wanted a rational number to be unique, I would say divide out any common factors. Does that make sense to everyone? Okay, so in general, when I talk about a rational number, I'm also going to assume that I have no common factors. And that's very important in this proof that we're going to do, because we have to find a contradiction, and this assumption of no common factors is actually what we're going to contradict. Well, that's a trick, I'm telling you right now. Okay? So what we want to do is prove that square root of 3 is irrational, and we're going to do it by contradiction. Because what would we have to do if we wanted to do a direct proof? I would have to take every combination of every integer over every other one and show that it wasn't equal to the square root of 3. Raise your hand if you want to do that. Okay, good. We're going to do proof by contradiction. So we're going to do proof by contradiction. So I'm just going to write up here what we're proving so we don't forget. So we're going to do by contradiction. So what do you do with proof by contradiction?
Negate the conclusion.
I negate the conclusion. I don't actually have any givens in this particular problem, so we just have the conclusion and we're going to negate it and start with that. So what's the opposite of saying that square root of 3 is irrational?
Rational.
So my negation of the conclusion is square root of 3 is rational. And I'm going to write an abbreviation for rational. And I'm going to put negation of conclusion. So then we want to use the definition of rational to figure out what to do next. So rational means that we can write this number as a ratio of two integers. Let's say square root of 3 equals P over Q, where P and Q are in the integers and it's reduced. So they have no common factors, right? And this was because of the definition of rational. Now, I did tell you, so we said that they have no common factors, and I did tell you that that was what we were going to try to find, is that they had a common factor. So what does having a common factor mean?
They're both divisible by the same number.
Right, we have to find a number that divides both P and Q, if that's what we want to find for our contradiction. Any pair of things that were opposites would be good for a contradiction. In this particular proof, though, this is the first thing that we have that we might be able to contradict. We don't have anything else so far. So what we're going to do is we're going to figure out what are the factors of P and Q. So since we don't really work with square roots very well, we're going to square both sides, and we don't work very well with fractions. We're going to multiply both sides by Q. So if we do that, we get 3Q squared equals P squared. And that's just regular arithmetic is the reason for that. So we cross multiplied and squared both sides at the same time. Please do stop me if you have a question. So if I skip too many steps in one, just let me know. So now we do know a factor of what? We've written P squared as a product of 3 and Q squared. So P squared has a factor of 3, right? Because that's what factor means. I can write it as a product of the factor times some other integers.
Yeah.
So P squared, let's write 3 divides P squared. If you remember, I used this vertical bar to mean divides. So in other words, it's a factor of P squared. So this is by the definition of divisibility. Now, if 3 divides P squared, that means I can write P squared is equal to 3 times some number, and we'll say k, where k is in the integers. And that's also by the definition of divisibility. Yes?
That sign, that looks like a number sign. Is that a number sign, what you're drawing there?
A number sign.
Z.
This is a z with an extra bar.
Thank you.
So the integers are represented with a z with an extra bar in the middle. My handwriting might not be wonderful, so. So we wanted to find factors of p and q, right? So right now we just have a factor of p squared, and we're hoping that that will give us a factor of p. So if 3 divides p squared, do you think that it divides p? Probably does, because I couldn't get a 3 from p squared if there weren't any 3's in p at all, right? But let's do a little proof of that. So there is a theorem in mathematics that would tell you that, and that is that every number is a product of primes. And that means p squared is a product of primes, and if 3 is one of them, 3 has to be, since it's prime, it has to be a factor of p also. But we're going to do a different proof for that. We're not going to assume that we know that for this proof. So we're going to prove the next thing that we want to know. This is what we want. I'm going to write it down. We want that 3 divides p, but we don't have it yet. So we're going to prove a statement. We're going to prove if 3 divides p squared, then 3 divides p. We should be able to prove it, right? Because it makes sense. Yes?
Not work, or?
That's right, it doesn't work.
No.
So you can move up. There's more seats closer.
Is there another symbol we could use for that?
Divides?
Because that's going to be...
No, there is not. In this class, I'm generally going to give you mathematical symbols so that if you look at a math book or something, you'll know what they're talking about. And I'm going to use them correctly so that you know what they mean. Because it's important for you to understand the language that is being used in mathematics and in engineering.
Can I put that back up for a second?
Yes. I'll put that back. So what we're going to prove is that if 3 divides p squared, then 3 divides p. So remember that I said before that if we wanted to talk about divisibility, one way we could do it was to separate the numbers into categories and check divisibility for all 3 categories. So since we're talking about divisibility by 3, I'm going to talk about whether p is divisible by 3 or not. And then we'll see what happens. So if I divide a number by 3, what are the possible remainders that I can get?
0, or not 0?
So anything, say if I take n over 3, my remainders, I could have 0 as a remainder, I heard. 1 could be a remainder. Or 2. Can I have any other remainders? No, I can't, because if a 3 was a remainder, I could divide out another 3 and I would have a remainder of 0. So every number can be represented as 3k plus each of these possible remainders. So every number can be written as a product of 3 and a number plus a remainder. So the number 4 can be written as what? 3 times 1 plus 1. How about 61? 3 times 20 plus 1. So when I talk about all the numbers that are of this form, that's every third number, right? So the number that comes right after a number that's divisible by 3 is going to be of this form. So the numbers sort of cycle. So if I start at 0, that would be 3k plus 0, 3k plus 1, 3k plus 2, and then 3 would be another case. So that's actually, I'll just write 3 times 0 plus 0, 3 times 0 plus 1, 3 times 0 plus 2, 3 times 1 plus 0. And the next one's going to 3 times 4 is going to be 3 times 1 plus 1. And 5 will be 3 times 1 plus 2. And so on. And it cycles. So as j changes, the numbers will get bigger. But every number can be written that way. Does that make sense to everyone? So when we do a proof, and we talk about divisibility by 3, we'll group the numbers into categories. Numbers that are divisible by 3, numbers that have a remainder of 1, and numbers that have a remainder of 2. So we wanted to prove that if 3 divides p squared, that implies 3 divides p. That's what we want to prove. So I'm going to make a table for that. First I have to make a column for p. I'm going to make a column for 3 divides p. I'm going to make a column for the logical implication. Actually, 3 divides p squared. So I have to put p squared over here, 3 divides p over here, and p over here. Since p is the simplest one to work with, we'll start by filling out the values for p. So we'll put 3k here, 3k plus 1, and 3k plus 2. I may not have left myself enough room, but we'll see. So in the first case, 3 does divide p, and in the second 2, it does not. And the reason why it doesn't is because if I have a sum of numbers, if I have a sum of 2 numbers, and one is divisible by the number and the other one isn't, then the sum is not divisible. If both of them, if all the numbers in the sum are divisible, then the total sum will be divisible. And that makes sense because you can factor out the number that divides both of the terms. So if I wanted to sort of mark to someone that I knew what I was talking about, I would check that this one was divisible by 3 and say, oh, that's not, so the sum can't be. That's a little shorthand for myself. So now from p, I can write out what p squared must be. Over here, p squared must be 9k squared. In the second case, it must be 9k squared plus 6k plus 1. I'm just squaring the p values on the right. In the last case, I must have 9k squared plus 12k plus 4. So we're going to use that rule I just told you to figure out whether these are divisible by 3 or not. In the first case, I can factor out a 3 from 9k squared, so I know that 3 divides p squared. In the second case, I have a number that's divisible by 3 plus another that's divisible by 3. So this sum so far is divisible by 3, but the last term is not, so the sum itself is not. And the same thing in the last case, the first 2 are divisible by 3, the last one is not, so the sum is not.
Where did you get these? I understand where you got 9k squared from.
All of them, the rows correspond. With the values of p, I squared the values of p to get this column because p squared is on top. I'm squaring all the values of p. So I have 3k plus 1 in the second row, and I've squared it to get 9k squared plus 6k plus 1, and same for the last row. So let me just, one thing I want to do before I finish this is if I have 5 plus 1, can I tell whether that's divisible by 3 or not? Let's just say 5k plus 1. I can't tell because I have more than one term that's not divisible by 3, so I can't tell whether it is divisible or not. Sometimes it will be because 5 times 1 plus 1 is going to be 6, which is. But 5 times 0 plus 1 is going to be 1, which is not. So if I have any more than 1 that's not divisible, I can't figure out anything there. Okay? So that's why we break up p in cases of 3k's, because then we can get some 3's in there and start to work with them and figure out when things are divisible by 3 or not. That's why we didn't break it into 5 cases, like 5k, 5k plus 1, 5k plus 2, and 5 all the way up to 5k plus 4. The next thing I do is I fill out this logical implication, and since they're actually both the same, I know that the implication goes both ways, not just one, but we only need one way for this proof. So now we know that any time a squared number is divisible by 3, the number must be divisible by 3. So that's good, because then we can use it back in our proof. So let's look back at what we were doing, just to remind ourselves, because we got off track, to do this little table. Now from now on, anytime we have 3 divides p squared or 3 divides any number, we can use this. So say that the square root of that number must be divisible by 3 as long as they're integers in the first place. Okay, so what we were proving is that the square root of 3 is irrational. We had gotten down to here. We got a factor of p squared. We knew we wanted factors for p, so we had to check and make sure that if we knew a factor of p squared, it would be a factor of p. And it is in the case of 3. So we did prove that. This is proven, so we can put it into our proof. So we'll just write it as a proof line. So we're going to write 3 divides p squared logically implies 3 divides p, and then we'll use modus ponens with this line. Let me number my lines. 1, 2, 3, 4, 5, and 6. So let me move on here. If I use 4 and 6 together, what rule will give me 3 divides p?
Modus ponens.
Modus ponens. If I have an implication and I know the left-hand side is true, then the right-hand side must be true. So with modus ponens, sorry, that doesn't tell me. This is my side proof, right? So that would be see other slide. In this case, I would write 3 divides p, and that would be from 4 and 6 and modus ponens. Now we're going to have to go back to line 3 because we now want to find a factor of q. So that's the last time we had any q's, so we need to go see if we can do something with q, now that we know something about p. If 3 divides p, how can I write it? I can write it as 3 times some integer, right? So p equals 3j. That's from line 7 and definition of divisibility. So I'm going to use that with line 3 to give me 3q squared. I'm going to substitute in 3j for p squared. So that's going to be 9j squared. And that was 3 and 8 and substitution. And that's not a rule on your sheet, but everyone knows what substitution does. Now, do you see where we might be going with this? What do you think is next? I'm trying to find out something about q, so I'm going to do what to this equation? I'm going to divide out the 3 from both sides, and then I'll get what?
Q squared equals 3j squared.
That looks a lot like what we had before for p, right? Now q squared is divisible by 3, and by our side proof, that gives us that, what? We must have that q is divisible by 3. So by our side proof, we know that if, well, right now we know 3 divides q squared, and that's from line 10 and definition of divisible. So with these arithmetic proofs, your rules are not axioms on a sheet that I'm going to give you. They're rules that you know from arithmetic, like definitions of divisibility, rational numbers, doing regular arithmetic. So you don't need an axiom list because these are things that you should have been doing for a long time. So 3 divides q squared is by the definition of divisibility, and that means I can write 3 divides q squared implies 3 divides q. That was my side proof. I'll just write that in as my reason. And then by modus ponens, by 11 and 12, I know that 3 divides q. And remember that we were looking for common factors. In line 7, we said that 3 divides p, and in line 13, we said that 3 divides q. So we now have that 3 is a common factor of p and q, right? So I can write 3 divides p and 3 divides q on line 14, and that's from line 7 and 13 in conjunction. And that means that p and q have a common factor. And that was from 14 and definition of factor. Oops, sorry. And what is my last line of my proof then?
Contradiction.
That's a contradiction, right? Because I said before that they have no common factors, so that's a contradiction. I'm skipping a step of writing them both on the same line, and I'll just put since p and q have no common factors. right? So it's hard to see immediately from looking at that where to go. You know, if someone says, prove that square root of 3 is irrational, but if you start the way that we learned to do proof by contradiction, so let's go back and look at the beginning again. We said we're going to do it by contradiction because we couldn't think of a good way to do it directly. Okay? Then we said, okay, proof by contradiction means I negate the conclusion. And then I was like, well, what does that mean? So I write what that means in terms of some numbers and some assumptions I want to make. Because then I want this to be a unique number, and that's why I assume they have no common factors. And all I see so far that I could contradict is that they have no common factors. So I immediately start looking for factors of P and Q. And I can't find any when there's any square roots in there or any divisible, you know, any divisions of integers. So I need to square both sides and also multiply, cross multiply by Q. So then I used my definition of divisibility because I knew I was looking for factors. But then that only gave me for P squared, so I had to do a side proof to find divisibility for P. And then I repeated the same process for Q to find that 3 also divided Q. So that was the most complicated arithmetic proof that you will have to do. So there's another way to do proofs where I can prove things for infinite sets, but I don't always want to talk about divisibility. Right? I might want to prove something is true for all numbers that doesn't have anything to do with divisibility, and then I don't know how to break up the numbers in such a way that I can prove something for each set. Right? So what I just did is I broke them down into sets that were mutually exclusive and then proved the property for each set. So if I can't do that with numbers, I might need to do a more complex proof. But before we do one that doesn't have divisibility, let's do another one since even numbers are pretty easy for us to understand. But let's do a proof by induction. And I'll tell you what induction is while we do it, but show you by example because it's a little bit hard to understand without seeing an example. So let's prove that same thing we did before. Prove n squared minus n is even. But we're going to prove it by induction. Now, by induction means that what we're going to do is we're going to prove it for some number, some starting point, and then we're going to assume that, and we're going to prove, that's what we're going to do. We're going to prove a basis. So we're going to prove that n squared minus n is even for a starting value of n. And then I'm going to prove an implication. I'm going to prove that n squared minus n even logically implies that this statement for the next integer, which is n plus 1, right? So I'm going to put in n plus 1 everywhere I see an n. I'm going to prove that that is even. So I'm going to prove that implication. Now, if it's true for the starting value, and this implication is true no matter what n is, then by modus ponens, it's going to be true for all of the integers. Right? So if I proved it starting, so let's say starting value n equals 0. If I prove it for 0, then I can plug, if 0 squared minus 0 is even, then that means that 1 squared minus 1 is even, right? Just by plugging those in. And by modus ponens, since I know this side is true, I would know that is true. Because my basis will prove this, and modus ponens will give me this, since I know the implication is true. And that means that the next one's going to be true. 1 squared minus 1 is even is going to imply that 2 squared minus 2 is even. Right?
How do you know your implication is true?
My implication is true because I'm going to prove this one. Once I prove it, sorry, that goes out. Once I prove it, then it proves it for all integers. And if someone hands me an integer, I can go start from 0 and go all the way up to the number they want. And I have a proof. So I basically would start with my basis and use modus ponens and the implication that I have over and over and over again until I would get the number that they wanted. So if someone gave me 24, I would have to do 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 23. And then 24 would be the last time I use modus ponens. Okay, so what I like to think about, so we're going to do this proof in just a second, but what I like to think about for induction is you're proving to someone how to walk up some stairs, you have to do two things, right? You have to get the person to the spot marked X, right? Then you have to show them how to go from one step to the next, no matter what the step is, because you don't necessarily want to go with them up all the stairs, right? So they have to get to the bottom step, and they have to be able to get from one step to another, or basically they have to get on the first step. Let's say this would be my basis, and this is called the inductive step. So in the inductive step, I assume I'm at the nth step, and I prove that I can get to the n plus first step. So that's basically like proving something in the middle. I prove them how to get to the bottom, and then this rule for going from one to the next, and that will get you as high as you need to go, because you start at the bottom, and you would iterate using your inductive step over and over and over again. So that's how I think of induction, as going up steps. If you leave out either part, then the person is stuck somewhere, right? If I leave out the basis, they're not even on the staircase. They can't go anywhere without that, right? They're not even at the staircase. They don't know the address, right? That would be like telling someone to go to the course web page and go to the notes page on the web page and never telling them what the course web page was. It's completely useless, right? Or if I tell them where the home page is and there's absolutely no links on there, then they still can't get to the notes page. So you have to give both pieces of information whenever you want to do induction. And this also is going to be true when we start to talk about recursion. Recursion is a really important concept in computer science. We're going to get our introduction to that in this class. And we're also going to be using induction together with it because they work the same way. Okay, so let's try this little proof we were going to do, n squared is even, by induction. We'll have to start with a basis. So we're going to start with n equals 0. Normally we're going to prove things for positive numbers, positive integers, because in discrete math we're usually not talking about real numbers. We don't need to worry about someone putting in 3.1 inputs into your program. Okay, they're going to do whole inputs, and if you get part of one, you'll throw away that part. Okay, so let's start. We're going to prove n squared minus n is even for n greater than or equal to 0. This tells me what my basis value needs to be. So in an induction proof, this is what I want to see on your paper. I want you to write the word basis so I can find it. Then tell me what value you're going to use for your basis. And then this is a predicate that has a variable in it, right? I usually think of this as p of n. That's what I'm going to prove. Okay, so I need to prove p of 0, right, which is equal to 0 squared minus 0 is even. I need to prove that that statement is true. 0 squared minus 0 is 0, and so 0 is even is a true statement, and I'll check it off. If it's something you can look at and think, yes, that's true, you can check it off. The next step, remember that when we do a proof, so we remember that our next step was to show that if we know p of n, then we know p of n plus 1 is true. We have to prove that statement, right? And whenever we do a proof, we assume that the left-hand side is true, and we show that the right-hand side is true. That's what we've been doing all semester long whenever we do proofs. So what we're going to do is we're going to assume p of n is true, so we write down n squared minus n is even. That's my given. And then we need to prove, and I want to see all of these statements written on your paper, prove p of n plus 1, and that is that n plus 1, quantity squared, minus the quantity n plus 1, is even. Sometimes I'm going to rewrite my proof statement just to make it a little easier to read. But the first time you write it, it ought to be just plugging in. Everywhere you see an n in the assumed statement, you want to put n plus 1 in the proof statement. If you notice, I didn't just add 1 to this pn. I plugged in n plus 1 in place of n. That's because p of n is a function of n. And the input, I think of functions as like the post office. You send a box, so p of n is a function, and I think of this p like the post office operating on some mail that you put in the mailbox. Whatever you put in this box or this package, that you send to them, they can't do anything to the inside, but they can do whatever they want to the outside. Okay, so if I do P of n plus 1, that's like a little package, and everywhere I had an n before, so this was n squared minus n is even. Okay, everything that's done to that package, I have to do this package. So I take my n plus 1, and I have to square it. And I leave it in the package, I square it, and subtract it again. So whenever you see any function, the thing that comes in the parentheses is an input, and you can't do anything to it. And you have to do the same thing to that as was done to n in the original function definition. So P of n plus 1 is usually not equal to P of n plus 1. So I want you to be really careful about that. So let's go back to our induction, unless there's some questions about this. This is really, you have to be very careful with function notation and use it properly. Okay, our proof is here. This is really, all of these steps are very important. You need to have a basis and prove it. You need to have your assumed statement and your proof statement. If you've written all of this, you're going to get 60% of the credit for a problem in this class. So I'm emphasizing this because I'm going to go grade your paper like this. 2 points, 2 points, 2 points out of 10. If you got all of these statements and you haven't even done hardly any arithmetic yet, you've got 60% of the problem. Okay, so the idea is I want you to get the form of induction and understand why it works. It works because of modus ponens, and because we have a basis and we have an induction step. So the induction step is assuming this and proving this. So we have to have all three of these things, because otherwise we won't have proved this and we won't be able to use modus ponens if we don't have a basis. Okay, so we have to have all of those steps. So let's now do this proof. I'm going to scooch this up.
Can you repeat where that P of n plus 1 comes from? Where that P parentheses n plus 1?
Well, in the problem definition, P of n is the statement that n squared minus n is even. That's a predicate that has a variable n. So P of n plus 1 is the very same statement, except for wherever I have an n, I have to plug in n plus 1.
Right, but where does that come from?
It comes from my problem definition right here. And this comes from that I have to prove this statement for induction to work.
Okay,
That's the definition of induction. Right, that was the step jumping thing. So I have to prove P of n logically implies P of n plus 1. Because that's the same as saying an if-then statement, right? So let's go back to our stair-stepping picture. I should have put P's on here. I really have to say that the predicate I'm proving for n is true at the nth step, and the predicate that I'm proving is also true at the very next step. Okay, so this would be some P of some n0. It might be a different starting point for different statements. So it might not always start at 0, although that's a nice, easy starting point for most things. Because algebra with 0 is very easy.
If you were doing an odd, if you were doing like divisible by 3, would you start at 1?
If I was doing what?
Like divisible by 3, like it was odd?
I could still start at 0.
Yeah.
It doesn't matter. Okay, so for this one, I need to now prove that n squared plus 1 squared minus n plus 1 is even. So let's write this in terms of, so this is P of n plus 1. I know that, just to remind you, I know from my assumption that n squared minus n is even. So if I can pull that out of this sum, then I'll know that part of it is even. And I'm hoping that the rest of it will have a 2. Okay? Because 2's tell me that we have even numbers. So if I have a sum of this plus some 2, some product with 2 and something else, then I'll know I have an even number. So I'm going to write, sorry, I put a squared in the wrong place. That was n plus 1 quantity squared. So that's n squared plus 2n plus 1 minus n minus 1 is equal to the statement I'm trying to prove, is even. I can get an n squared and a minus n, and let's group all those up at the front. So that's equal to n squared minus n plus 2n and the plus 1 and minus 1 cancel. So I have three terms, 1, 2, 3, 1, 2, 3, and I've moved them around. So I know, so this is equal to 2k. Let's say that n squared minus n, since it was even, it's equal to 2 times a number k plus 2n, and that's equal to 2 times k plus n. So therefore, n plus 1 squared minus n plus 1 is even. Now it's really important that I used my assumption. You're going to be doing that every time you have an induction. You're going to be looking for something that looks like p of n. N squared minus n was a term that I had in my assumption step. So it's very important, and I did a substitution for that. I used the fact that n squared minus n was even. I used that here to show that this total sum is even. So we had two choices with this one. We could do an arithmetic proof, or we could do a proof by induction.
Would you have to give reasons for each of those steps during a proof?
No.
Is it mostly arithmetic anyway?
It's mostly arithmetic. This was definitely arithmetic, right? In order to be able to study from your work, you might want to give reasons for every step that you did. This is by my assumption, right? I did a substitution in. Actually, this was just arithmetic again. By assumption was for the next step. So both of these first two steps were arithmetic, then by assumption for the next step. And this is for definition. So this conclusion from here is the definition of even. So you should be able to write down the reasons for every step that you do. If you can't, then you've done a magic step and you need to go back and figure out what it was.
That's that 2 times a number reason.
Right, because even means that I can write it as a product of 2 and some other integers. And k plus n is an integer because integers are closed over addition. So I have lots of assumptions going on in these proofs that I don't need to write out because anyone who's looking at them will know that I'm talking about integers that are closed under addition. Okay, are there questions about this proof? We're done because we did a basis, we did an assume and proof statement, and then we showed that our proof statement was true using our givens. Yes?
So for induction, we only have to prove it for basically 2 cases, n and n plus 1?
We prove it for a basis, which was 0 in this case. So we have 3 things that we do.
Okay.
We prove it for a basis, then we assume that it's true for an nth step, and we have to prove that it's true for the n plus first step. So we have to prove p of n plus 1. So we really only have to prove 2 things. We have to prove p of 0 or p of whatever your start is, plus proving p of n plus 1, assuming that p of n is true. Yes?
No, you've made this look very simple. What are the real questions like?
Okay, that's what we're going to move on to next.
Second step, you said proof for basis, and then assume, right?
We assume p of n is true. So we'll put back the first slide so you can review. We assume p of n is true. We show that p of n plus 1 is true. And I want all of these statements written out. I don't want you to write just assume p of n. I want you to write what p of n is. And I don't want you to write just p of n plus 1. I want you to write what p of n plus 1 is, because most of your mistakes will come by not using the correct thing that you need to prove, or by not assuming the correct thing. So I want you to write them all out so that when you're doing your work, you'll be able to look back at them. The main reason for showing this is to know when you're done. And the main reason for this is to know what you're starting with. So you need to do both of those, because we can't solve any problem without knowing where we start and where we're going. Right? That's what we always did in our proofs, for our logic proofs, right? We had givens, we had what we were proving, and to get in between, we had to use the givens. And we knew where we were going, otherwise we would just be sitting there writing things that were true but not going anywhere. Okay, and sometimes we did that. Right? And proof by contradiction, we have the same thing. We had some givens, we had a negation and a conclusion, and we knew where we were going to a contradiction. So in every case, we want to transform a problem into something that we know where we're starting and we know where we're going to. We may not know how to get there yet, but at least we can write down those things, and that's very important. Okay, so let's do another problem. So we're going to be doing a lot of arithmetic-looking problems, and that's important because when you're doing analysis of algorithms, you're going to need to know how to deal with summations. So I'm going to do one and then show you how it's applicable first. So I'm going to first do one and then show you why it's useful. 1 plus 2 plus dot 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 plus n is equal to n times n plus 1 over 2 for n greater or equal to 1. So before you do a proof, a lot of times it's useful just to make a chart for yourself to verify that you think it's true. Because you don't want to do an induction proof on something that it's not true because you won't ever be able to finish, right? So you should make a table to verify to yourself that this is true, because Tiffany can make mistakes. Okay? So let's make a table of n and our function. What's this dot 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 thing mean? It means continue in the same pattern as you were doing, which means I'm going up by 1 every time. And so how many terms are in the sum? N terms, right? So here, if n equals 1, I have 1 term in the sum, and it's just 1. If n equals 2, it's 1 plus 2, which equals 3. If it's 3, it's 1 plus 2 plus 3, which is 6. If it's 4, it's 1 plus 2 plus 3 plus 4, which is equal to 10. And 5 is 1 plus 2 plus 3 plus 4 plus 5, and that's 15. So let's go back and fill in the other part of the table, which would be the function that we think matches with this, n times n plus 1 all over 2. So in this case, n times n plus 1 over 2 is 1 times 2 over 2, which is 1. Right? 1 times 2 over 2 equals 1. In this case, that's 2 times 3 over 2, which is 6 over 2, which is 3. In this case, I have 3 times 4 over 2, which is 6. Looks pretty good so far. In this case, it's 4 times 5 over 2, which is equal to 10. In this case, I have 5 times 6 over 2. That's equal to 15. So I'm pretty well satisfied that Tiffany didn't give me a bogus problem, and I'm ready to solve it. This also helps me get what?
Basis.
My basis. I've already proven a basis here, right? I can just use these values for n equals 1, and I will get my basis. Okay, but it's important for you to write the word basis, n equals 1, and write it out. So we're going to do that next. Anytime you have a problem like this, though, it's good to write out a table. So I'm going to do the proof, but before I do the proof, I would like to write another notation for this, because I don't like writing dots. Because it doesn't really specify, it requires a person to look at it and tell what do the dots mean. Because I might have done something like n plus 2n plus 3n plus 4n plus 5n, and that's a pattern. That's not adding 1 every time, right? So that's doing something different. So I want to use a notation that tells me what I'm doing, and everyone can read it, and everyone interprets it the same way. And that's what we're going to talk about is summation. Summation's really important because you're going to end up with summations every single time you're doing an analysis of a program to see how many clock cycles it's going to take to run your program. So this is the notation. We have summation. That's what, when I see this symbol, I think summation. It's a Greek letter, sigma. Okay. I'm going to put at the bottom, I'm going to put a variable. It's going to have a start value. Let's just start with 1. And let's go up to n. That's my final value. And then I'm going to put some function of k in here. Now k changes because k is a variable. So when I see this, I think of this as a for loop. For, and let's just actually just put start here. Instead of 1, I'm going to put start, and instead of n, I'm going to put end. Okay, I'm going to think of this as a loop. For k equals start to end, I'm going to do an initialization first. I'm going to do sum equals 0, and then I'm going to say, inside this for loop, sum equals sum plus f of k. So if you haven't seen pseudocode before, it's fairly easy to read this. For all the values of k, add to sum f of k each time. So k changes each loop. Okay, so let's do an example. The problem we were looking at was 1 plus 2 plus 3 plus ... plus n. So if I want to write that as a summation, what's my start value for k?
1.
So I would have that as a summation. K equals 1, and what's the ending value?
And
N. And what is the function?
N into N
It's
plus
just
1.
k, right? It's just k because the first time the number in there is 1. The second time the number in there is 2. The third time the number in there is 3. So each value, that's just equal to k. It's important to write that because this is a much larger sum, right? N is a fixed value there, and k changes. What is this value?
and the
That's adding into itself n times. So this is n squared, right? Because it's n times adding into itself, right? Because this goes through this loop n times, and I would add n plus n plus n plus n times. So adding n times is n times n. So this is different, right? And I said what we're going to prove that was equal to n times n plus 1 over 2. We're going to prove it. So these are two different numbers. N squared and n squared plus n over 2 is different. So it's very important to write the correct thing inside your summation. If you write n inside, then you have a much larger sum. Because each term is larger, right? If I compared 1 plus 2 plus 3 with n plus plus n of them, and usually if I use that notation, I'm going to use a curly brace and say that there's n terms to let myself, this is much bigger than that, right? The sum with all the n's is much bigger than the sum with things that are lots of terms that are a lot less than n. All right, so let's move on. And
Why is k, the next one where you have n squared, why is k equals 1?
why does k equals 1 in this summation?
No, the other one, this one.
In this summation?
Yes.
This just tells me how many times I'm going to add n together, because the thing on the inside doesn't depend on the variable,
Okay.
right? It just tells me how many times I'm going to go through and add this thing on the inside.
It's the starting value of the loop.
K equals 1 just tells me when I should start. I could start at k equals 1500 and then go up to 1500 plus n minus 1 if I wanted to do exactly n times. Starting with 1 is a lot easier to understand that I'm going to do it n times. In this case, it doesn't matter that I start with 1. I would just need to do the difference between them is n, right? In this case, it matters because the function on the inside depends on the variable. So it doesn't matter which one, you just count. On this one, it doesn't matter, you just count the number of times you go through the loop. Okay, well, let's do an example just to make it a little easier to understand. Okay, so for k equals 1 to 1, that's just the summation from 1 to 1, right? Sum, and we're going to assume that sum is initialized, sum equals sum plus k, because that was the summation we were talking about, adding k every time. So how many times do I go through this loop?
once.
Just once. So sum is equal to what?
1.
Right, it's equal to sum plus 1, and sum started as 0, right? So sum equals 1. At the end of the loop, this is my final value. And that's what the summation is. So this is for the summation k equals 1 up to 1 of k is equal to 1. Let's try it for a larger one. K equals 1 up to 3. Let's do 3 of them. 4 of k. K equals 1 to 3. Sum equals sum plus k. So I would have to do 3 steps, right? K equals 1. Sum equals 1. K equals 2. Then sum equals what? 1 plus 2. K equals 3. Sum equals 1 plus 2 plus 3. And so my final answer is 6. At the end of the for loop, my sum was equal to 6. So this summation here is equal to 6. So whenever I see a summation, I think of a for loop where k goes up by 1 every time. Automatically, for loops always increase by 1. If you haven't done any coding, that's what it does unless you tell it to do otherwise. And summations are just like that. The index, the variable, is called the index, and it is always increasing by 1. So even if it looks like my summation has a function in it, if I had to write this out, k still goes up by 1 every time. Okay, so if n is equal to 1, this is equal to 2 plus 3, right? If n equals 2, what's it equal to? 4 plus what? 5 plus 6. The first number is 4 because it went from 4 to 6, but k goes up by 1 every time, so it doesn't go 4, 6, whatever. Okay, n equals 3 is what? Starts with 6 and ends at 9, right? So it should be 6 plus 7 plus 8 plus 9. N equals 4 should go 8 to 12. Right, so the number of terms here, I can double check that I've written the right summation by checking the number of terms that I have. The difference between 3n and 2n is n, right? So it should be n plus 1 terms because I have to take the difference and add 1. So this is n plus 1 terms, and I can verify that all of these are correct because each of them has n plus 1 terms. This has 2 terms, that has 3, 4, 5, and so on. And each value should go up by 1 every time. If this was f of k on the inside, it would be f of 2 plus f of 3, f of 4, f of 5, f of 6, and so on. So you would have f's on all of those. And just while I have f notation here, a lot of times we'll write just a subscript on a variable to let you know that we're plugging in 2 for the function. So f parenthesis 2 is the same as f sub 2. So it's going to be a little easier for notation sometimes when we're writing summations. Let's go back to the problem we were trying to solve. So we wanted to prove that 1 plus 2 plus dot 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 plus n equals n times n plus 1 over 2 for n is greater or equal to 1. Now before I start one of these problems, I usually write it in a summation form. So I'm just going to go ahead and write, this is summation k equals 1 to n of k equal to n times n plus 1 over 2. And that helps me because then when I'm doing my proof, it's a little easier to plug in for n and n plus 1. Because sometimes these get a little hairy and you're not sure exactly what to do if you don't know what these little dots mean. So when you write it as a summation, there's no ifs, ands, or buts about it. We know what it means. We know it's just like a for loop, plugging in k for the variable. Now I have to do my basis. N equals 1. So I have the summation k equals 1 up to 1 of k. That's equal 1. And then I need to check, is 1 times 1 plus 1 over 2 equal to 1? And it is. So these two things are equal, so I'm done with my basis. My next step is my assume step. So I'm going to write summation, and this is going to feel redundant to you because you're basically going to write again the statement you're trying to prove. You're going to write it again, and if you don't like it, well, you only have to do it a limited number of times before you stop taking this class. So just write it again, and it will make your graders happy. And then we write our proof statement, which is to basically copy the assume statement over, but we're going to plug in everywhere we see an n, we're going to put n plus 1. So what does this one look like? K equals
1 to n plus
1 up to n plus 1 of what?
Okay.
K. This is where it's important. If you accidentally put an n in there, you might accidentally put an n plus 1 in here, and then I won't be able to prove it. Okay, so make sure you have k's in the correct place. That's equal to what?
N plus 1,
N plus 1 times
N plus 1.
n plus n plus 1 plus 1, which is n plus 2, all over 2. We have 60% of our credit so far. So the hard part comes next. This is the part you memorize. Basis, assume, prove. Basis, assume, prove, and you'll do it enough times that you will definitely be able to get it. And in the packet are many examples of these kind of proofs with summations. Packet 3.1 is up on the web, and you can take a look at these. There's lots of examples that have basis, assume, prove. Nice and underlined. The algebra is done, so you can see some practice problems. So let's try this one. What I usually do is I start with the left-hand side. That's what LHS is going to stand for. Left-hand side of the proof statement. The next thing I do is write it in terms of the assume statement. And this again is just like we've done direct proof with our propositional calculus, because we were normally looking at what we were trying to prove and finding things in our givens that looked like what we were trying to prove. So what we're trying to do is make our given look like what we're trying to prove. So then we're going to substitute. So we're going to write it in the terms of the left-hand side of the assume statement, and then we'll substitute the right-hand side of the assume statement. We'll substitute that in. And then we'll usually do arithmetic to get the right-hand side to look right. So those are some rules for you to remember, because they'll be the same for almost every induction proof that you do. And that'll make more sense once we do it in this problem. So left-hand side, you'll be able to keep them straight better after we do a problem, and you'll see what we're talking about. Everybody done with that? So what we did is we're going to start with the left-hand side of a proof statement. So we're really starting the proof. All that stuff beforehand was set up. So now we're going to do k equals 1 to n plus 1 of k. And we need to write it. I'm just going to go ahead and write my assume statement, and then we're going to have to fix this so the equals is actually true, because it's not true right now, right? So right now it's not true. I have to do something to the right-hand side to make it true. What do I have to add to the right-hand side to make this equal true? This is a for loop that goes for k equals 1 to n plus 1. This is a for loop that goes k equals 1 to n. So all I need to do is one more step of the for loop where n plus 1 is. So all I have to do is add n plus 1, and then those two statements will be equal. In other words, this might make a little more sense, or it might make less. I have to do one more step of the for loop of the exact same form, but k has to be equal to n plus 1. And this is a really good way to write it, because any summation can be broken up in any fashion that you want. You can break it up and stop the for loop and restart at the next value. So this was just for your own practice. You'll be using that later, that kind of notation. So all we had to do was add n plus 1. Now remember that we said we had to substitute in the right-hand side for the assumed statement. So this was the left-hand side of what we assumed, so we're going to substitute in what we knew it was equal to, and that was equal to n times n plus 1 over 2, but we have to leave this n plus 1 on there. So the left-hand side of what we're trying to prove is still here on the left-hand side. Now we're going to try to get that to look like what we want to prove, which is n plus 1 times n plus 2 all over 2. And I'm remembering back from my proof statement, so you have that on your paper, you can look at it. All right, so what I need to do is get a common denominator so I can add these things, right? So I have to multiply this one by 2. Now this is where it's a little bit hard for people because they haven't done that much algebra in a while, and factoring with letters is a little hard. But I look at this and I see that there's an n plus 1 in both of my terms. I could move that n plus 1 out to the front and then be left with the stuff that was next to it. So let's move the n plus 1 out to the front, and then we're left with n plus 2 if we factor an n plus 1 out of both of those. And lo and behold, that is what I wanted to prove. That's the right-hand side, so I check it off and I'm done with my proof. So therefore, P of n implies P of n plus 1, and I proved my basis. So by induction, our summation can be written in a closed form, so I can write this. So therefore, summation k equals 1 up to n of k equals n times n plus 1 all over 2 is true for n greater or equal to 1. Because I did prove my basis and I proved my inductive step. If I do both of those, it's proof for all integers past my starting point. This is really handy. Really handy because now every time you see a summation where it's 1 plus 2 plus 3 plus 4 all the way up to some ending value, whatever the ending value is on top, you plug it into this formula and now you know how to calculate that number without having to do a bunch of sums, which is a pain. So are there questions about that? There are many examples in Packet 3.1. I'd like you to look at those and try some of them. Your next homework assignment is going to have several problems of this form, and we'll do some more in class next time. And we're going to do some of those next time, and we'll probably also move on to recursion. So try some of these problems, and also I'll be putting up Packet 3.2 for you to look at pretty soon, so you'll be able to look at stuff about recursion very soon. Thank you.